Okay, so you just completed a graph, the table of values from this problem right here, right in the Desmos, right from the website. What I'm going to do here is just go over filling that table in, and then I'm going to add a part B to this question, and then also a part C. And then I'm going to ask you to go back to that graph and put an equation that we developed. So I'm going to show you here how that problem relates to our goal here, which is learning about exponential growth. Okay, so if I just read it, the problem here, we've got bacteria in a petri dish that grows, so that triples every day. Currently the bacteria has a population of 100. We want to determine the population after each of the first 4 days. So you did this in your last, in the Desmos graph. So at day 0, we're talking about the beginning. We got 100 bacteria in the dish. At day 1, it's tripled, so we've got 300. At day 2, that's been tripled, so we're at 900. Day 3, that's been tripled, we're talking about 2,700. And if that's tripled, on day 4, we're talking about 8,100. Okay, so that's the table. That's part A. If you plot those points in Desmos, it's going to show a particular growth, which is exponential growth. So let's look at part B. Part B is something new. We're going to calculate what was called the finite differences. And the finite differences are like first differences, but notice the first differences, this grows by 200 and then 600. It's not constant growth, and that's why it's not a linear relation. But finite differences is, instead of a common difference, it's a common ratio. So what we're talking about is, instead of taking 300 and subtracting 100, we're taking 300 and we're dividing it by the one before it, 100. And we should get a common ratio all the way down. Notice, take 900, divide it by 300, the one before it, and we still get 3. Take 2,700 divided by 900, you get 3. Take 8,100 divided by 2,700, you get 3. If we divide those common, or those finite differences, if all of them are common number, like we get 3 here, then this tells us this is an exponential function. The problem is growing exponentially. Okay, so let's continue. It's the same problem we have here, but let's answer part C, which is coming up with an equation for this function. So that's our goal here, is to come up with an equation. Let's go back and look at the table. I'm going to rewrite these in a particular way. Notice we're multiplying by 3 here every time. So this is really this is really a 100, which is just 100 times 1. Okay, this one is 300, which is really the one before it, times 3. And this one is really the 100 times 3 times 3, so that's 3 squared. And this one is really the 100 times 3 times 3 times 3, which is 3 cubed. And this is really the 100 times 3 to the power 4, 4 threes. And so notice, we've almost got the exact same expression every time. The only thing that's changing here is our exponent, and it is matching the day number. If you notice, there's 1 here, it's 1 3. A 2 here, it's 3 squared. A 3 here, it's 3 to the power 3. So notice we could write an equation here, because the only thing changing is the exponent, is by the exact day number. So if I let P be the population, and I let, say, N be the number of days, then I could write an equation for the population. The population equals that 100, and then it's tripling, so I've got a factor of 3, and then the only thing that's changing is that days, and that was our exponent. So here's our equation to model that growth, that it's 100 times 3 to the power of n, and our variable is the exponent. So to answer part D, I'd use my equation to predict the population after 2 weeks. That's the nice thing about an equation. I now have this times 3 to the power of n, which is the number of days. Well, 2 weeks is going to be to the power of 14. and then you could use your calculator to crunch this out. 100, you go 3 to the power of 14, large number, times that by 100. Then we get 478,296,900. Let's look at another problem. In these sets of problems, we're going to look at the scenario and we're going to come up with an equation for each scenario. So notice this one is a different bacteria culture. It starts with 10 and it doubles every day. So if I use the same variables, this population is going to start with 10 and then it's doubling every single day. So instead of multiplying by a factor of 3, we're multiplying by a factor of 2, and then it's going to multiply by a factor of 2 for every single day, and we'll let n again be the number of days. So that's the equation for that scenario. For this scenario, I've got an antique is currently valued at $200. It increases in price by 20% each year. So this time it's not increasing by a full 100% each time. It's only increasing by a part each time. So after 1 year, it's not going to double in value. It's only going to increase by 20% in value. So if I say it's the value for V, like V for the value of the antique, that's going to equal, well, it starts at 200, so we're going to take 200 and then we're going to multiply by some growth factor, and this growth factor is only 20%, so it's growing by 20%, so I've got to say it's 1 and then 0.2, and that's going to be that 100, it's like 100% plus this 20, it's like the original amount of 100% plus 20% more, so that's the 0.2 part, and then if each year we might be n again for the number of years. Similarly, it's another percentage. So this car is valued at the 15,000 to start with, and then it depreciates at 24% per year. So it loses value 24% per year. So it's like it starts, you could look at it this way, it starts with 100% as a value, which as a number is 1, and then it loses 24% of its value every year. And so if I rewrite that in the next line, we'll simplify that in the next line. But this is happening every single year, and it's losing a percentage of the year beforehand. So we're going to let n again be the number of years. So this simplifies to 0.76 to the power of n. So this is an equation that would represent the car depreciating by 24% every year. One final one in this video. So now we've got a bacteria culture that has 40 cells, but it triples in size every 5 days. So let's start here with P for the population. It starts with 40, so it's going to be 40, and then it's tripling. So we've got a factor of 3. It's going to be like the first day be 40 times 3 after every 5 days. So how we're going to handle this, though, is it takes 5 days to triple, and if we want n to be the number of days, then it takes 5 days. This has got to be a 5 before, this has to be a 1 before it triples. So the exponent has to be 1 in order to take 40 and multiply it by 3. That has to occur every 5 days. So what we're going to have here is the exponent can't be just n. It can't be just n because that means after 1 day, then it's 40 times 3, which is tripling. We need this to be after 5 days, it triples. So I'm going to erase that. We need this to be after 5 days, this exponent then becomes 1. So we're going to write n, which is the number of days, divided by 5 as the exponent. And therefore, notice after 1 day, the exponent's a fifth. After 2 days, it's the 2/5. But notice after 5 days, that exponent would then be a 1. And then that would allow us to take 40 and times it by 3, which allows it to triple. And then notice after 10 days, that exponent is 2. After 15 days, that exponent is 3. And that allows it to triple on those number of days. So this equation, let me write it a little bit nicer. Would be the population of that bacteria tripling every 5 days.